Generative artificial intelligence is a buzzword you will hear everywhere these days, but its true meaning is often misunderstood. Many people mistakenly think it's a completely new type of AI, often confusing it with ChatGPT or other large language models. In fact, generative AI differs from traditional AI in that it doesn't process existing data, but is used to create new data from scratch. In this video, we're going back to the roots of generative AI to explore one of the fundamental techniques for creating never-before-seen images, Variational Autoencoders, or VAEs. These models have not only laid the groundwork for understanding generative processes, but are also key components in modern architectures such as Stable Diffusion. But why do we even need such models? Why can't traditional deep learning models like standard autoencoders generate new images on their own? Let's dive in and find out. Autoencoders are based on a simple but powerful concept. They take data, compress it into a low-dimensional representation, and then reconstruct it back into its original form. While an image usually contains millions of values, the low-dimensional representation is usually a vector of 10 to 100 numbers. These representations live in a space with a more compact and interpretable form, usually called the latent space. If you're not familiar with these concepts, check out the previous video where we cover the basics of autoencoders. Now, if we have a trained autoencoder capable of reconstructing images from their latent representations, a natural idea for generating new data would be to randomly sample points from this latent space and run them through the decoder. But here's the catch. In most cases, this approach will not produce useful results, mainly because the latent space is disorganized and irregular. So large areas of it will not produce meaningful decoded images. Another approach could be to take an encoded image and then sample points that are in the neighborhood of its latent representation. This should give us images that resemble the original, right? Well, not exactly. The latent space is so poorly structured that even nearby points often don't correspond to meaningful variations of the original image, and if we sample points closer to the original image, we just end up with the same reconstruction. So what's the solution? Well, ideally we want a latent space that's nicely organized, where sampling points lead to coherent new images. Let's see how VAEs do it. Well, first, let's start by giving you some context. The man behind the creation of variational autoencoders is Kingma, who first introduced them in 2013 in his groundbreaking paper, Auto-Encoding Variational VAEs. Well, if you haven't heard of Kingma, he's also the mind behind the Adam optimizer, which is a widely used optimization algorithm for training neural networks, and a big part of why deep learning has made such huge progress in the past decade. Kingma's research focuses primarily on deep learning and Bayesian statistics, which are precisely the two core elements of variational autoencoders. Before we can dive into the theory behind VAEs, we will quickly cover some basic Bayesian notations and properties. If these are new to you, don't worry, I'll break them down step by step. Let's say we have a random variable x, which can take any value between 0 and 10. When an event occurs according to the probability distribution of x, we refer to this as sampling from x. Now, here is what we call the probability density function of x, which basically tells us the probability of a sample being any of the values between 0 and 10. We usually note p of x, the density of x. An interesting quantity describing the distribution of x is its expectation, usually noted e of x. It is basically the average value that you can expect when sampling from x, and it can be computed using the integral of the probability density function. Now let's consider two random variables, x and z. What you see here in 3D is what we call the joint probability distribution of x and z. This represents the probability of each possible pair of events occurring together. Of course, each variable also has its own individual probability distribution, known as the marginal distribution. As before, we denote the marginal distribution of x as p of x and the marginal distribution of z as p of z. Note that these are two separate densities, although we write both densities with a p. An interesting property of the joint distribution is that we can use it to compute each of the marginal distributions. This process, known as marginalization, involves integrating the joint distribution with respect to the other variable. For example, to find the probability of sampling a specific value according to x, we integrate the joint distribution over all possible values of z. And similarly, to determine the probability of sampling a value according to z, we integrate over all values of x. The final concept we need to cover is conditional probabilities. The term p of x given z represents the likelihood of the data x given the latent variable z. As you can see, it is expressed using the joint distribution and the marginal distribution of z. Essentially, it's like taking a slice of the joint distribution and normalizing it by the probability of sampling that value of z. For instance, if we want to compute p of x given that z equals to 3, we simply look at this slice and normalize its values by the probability that z equals to 3. Finally, p of z given x represents the probability that the latent variable z was present when we sampled the data x. We compute it just like we did for the other conditional distribution. We look at the slice and normalize the values by the probability that x equals 7. Now that we've got the basics down, let's explore the ideas and theory behind VAEs. So our goal is to generate new data from a given distribution, p of x, which represents our dataset, for example, images. The problem is, we don't know the exact shape or properties of p of x. We only have access to some samples, for instance, images from our training split. To make working with p of x easier, we introduce another distribution, p of z, called the latent distribution. This distribution represents latent variables, vectors in a lower dimensional space that capture the core features of the data. Since these two distributions live in different spaces, we need mappings to connect them. The first mapping is called the posterior distribution, and it gives us the probability that a latent vector z was generated by a particular image x. The second mapping is the likelihood distribution, which, given a latent z, tells us the probability of reconstructing an image x from it. Now here's the idea. If we can sample latent vectors from the posterior distribution, those latents are likely to have been generated by images from our original data distribution, p of x. So if we can reconstruct these latent vectors back into images, we'll effectively generate new samples from our original data distribution. However, there's one issue. We don't know the exact form of the latent distribution p of z either, which makes all the computations intractable. To solve this, we assume that the latent distribution is in fact a normal distribution. This assumption allows us to compute the likelihood p of x given z, which measures how probable it is to reconstruct an image from a latent vector. But we're still missing an important part of the puzzle, the posterior distribution, p of z given x. This is where the variational part of the variational autoencoder comes in. Since we don't know the true posterior, we approximate it using a Gaussian distribution, which we'll call q of z given x. This Gaussian will have parameters, mu and sigma, that we need to learn, which is an optimization process usually known as variational Bayes. And here's where the magic happens. We'll train a deep encoder to estimate these parameters mu and sigma from the images. Then, we'll use a decoder to reconstruct images from latent variables that are sampled from the approximate posterior. But how do we actually train this whole autoencoder to approximate the posterior and then reconstruct images from it? Using Bayes' formula and some basic properties, we can derive this training objective for our autoencoder. For those of you who want to know how to derive this equation from scratch, we explain all the derivations in a bonus section at the end of this video. While this whole equation may seem a little daunting, it's actually quite intuitive. The first part is essentially a data consistency term, while the second part acts as a regularization. So this data consistency term simply measures how well our model can reconstruct an image x from its encoded version z. To ensure that z is taken from the approximate posterior, we take a real image and simply encode it. Conveniently, with all our assumptions, this likelihood term reduces to a simple L2 reconstruction loss, also known as the mean square error. So to estimate it, we simply take our latent and reconstruct it using the decoder, then measure the L2 between the reconstruction and the original image, just as we do for regular autoencoders. Now let's look at the KL divergence part of the equation. If you remember our previous video on latent space visualization, you know that the KL divergence is a kind of distance between two probability distributions. So this term measures how close our approximate posterior is to the prior distribution P of z. Since we chose P of z to be a normal distribution, this means that when we optimize the ELBO, we constrain the approximate posterior to take the shape of the normal distribution as well. To recap, the ELBO is the training objective of our variational autoencoder, and it is designed to ensure that the generated samples come from our original data distribution P of x. It can be thought of as a regularized reconstruction loss, with the first term representing the usual L2 loss, and the second term imposing a normal distribution shape on our latent space. Now that we've got the theory down, let's move on to the practicalities. So we have a theoretical objective to optimize, but how does an autoencoder actually implement these different distributions in practice? Let's quickly recap what an autoencoder does. It takes an input, compresses it into a lower dimensional representation, and then decodes it back into the input space. In a standard autoencoder, this compressed representation is a single point in the latent space. Now with variational autoencoders, things work a bit differently. Instead of mapping the input to a single point, the encoder converts the input into a probability distribution that we chose to be a Gaussian. Essentially, the encoder transforms the input data into the parameters of this Gaussian, namely the mean, mu, and variance sigma. Now, instead of representing our image as a single point in the latent space, it's represented as a Gaussian distribution. From this latent distribution, we sample points at random, and the decoder converts these sampled points back into the input space. We can then compute the different parts of the ELBO loss and backpropagate it through the network. But wait, can we really do that? How do we even backpropagate through the sampling operation here? Well, the thing is, we can't. This is where the reparameterization trick comes in. Instead of sampling directly from the Gaussian distribution, we introduce a random variable, often called epsilon, to handle the randomness outside of the network. This trick is actually pretty simple, but very powerful. First, we sample a random point from a standard normal distribution. This is our variable epsilon. Then we scale it by the variance of our approximated posterior distribution and shift it by its mean. It is just as if we sample directly from the posterior distribution, except that by using the reparameterization trick, the process becomes differentiable with respect to the mean and variance. This trick allows us to backpropagate through the entire network, enabling us to train the VAE end-to-end using standard gradient-based optimization techniques like Adam. In a typical VAE training, the process begins much like training a standard autoencoder. We start by taking an image and passing it through the network, which then generates a reconstructed version of that image. We then compare this reconstruction with the original image to measure how well the network is performing. But unlike a standard autoencoder, a VAE also outputs the parameters mu and sigma of the approximate posterior distribution. So we then calculate the Kullback-Leibler divergence between this posterior distribution and the prior distribution, which is just the standard normal distribution. The nice thing is that for two Gaussian distributions, the KL divergence has the following closed-form expression. So we just compute this quantity, backpropagate the combined loss, update the network's weights, and repeat this process for each image in our dataset. Now let's take a closer look at how the latent space of our VAE evolves as the training progresses. At the very beginning of training, the images are all encoded in the same region of the latent space. Then after a few gradient steps, the regularization pushes the latents to spread over a normal distribution. After 2 or 3 epochs, the Kullback-Leibler divergence is so small that the latent space hardly changes, but the reconstruction loss still needs to be optimized. After the training is complete, the latent space of our VAE looks like this, which is very close to the shape of a 2D normal distribution. Additionally, our VAE can now accurately reconstruct any digit it encounters. As you can see on the right of the screen, reconstructions are very close to the original images. But that's not all. The trained VAE also allows us to generate entirely new handwritten digits that weren't part of our original dataset. By sampling a random latent vector, we can create a wide variety of new digits, some realistic and some more creative. And we can also generate new images that resemble existing ones. To do this, we first encode our reference image into its latent representation, then sample nearby latent vectors. The closer the sampled vector is to the reference vector, the more similar the resulting image will be. As we move further away in the latent space, the generated images become increasingly different from the original image. Another interesting feature of VAEs is their ability to blend two images seamlessly. To do this, we first encode both images into their latent representations using the encoder. Once we have these latent vectors, we can create a convex interpolation between them. By adjusting the interpolation parameter alpha, we smoothly transition from one image to the other. This shows that the latent space learnt by the VAE is sort of continuous, enabling us to navigate through it and still generate coherent results. This is very different from simple autoencoders, where changes in the latent space often lead to meaningless or distorted results. Variational autoencoders, however, maintain a compact and smooth latent space, ensuring that most points within the normal distribution in the latent space will lead to plausible samples. Variational autoencoders are great, but of course they have their weaknesses, the most obvious being that they tend to produce very blurry images. For example, if we train a fairly large variational autoencoder on the Saliba dataset, it will still struggle to reconstruct the images efficiently. This dataset is composed of portraits of celebrities, with images around 5 times bigger than the previous digit images. As you can see with these 4 reconstructions, the faces are somewhat realistic, but the background is just a blurry mess. Note that this is not caused by the architecture of the network, but by the regularization term in the loss. And of course, if we randomly sample new data points, the problem persists. When VAEs first came out, they were compared to the state-of-the-art generative models, which at the time were GANs. As you can see, the images produced by GANs are much sharper, which made them more popular for a lot of tasks. And it hurts even more when you compare VAEs to the current state-of-the-art generative models, diffusion models, that are used in all image generation products such as Midjourney and Stable Diffusion. Another limitation of basic VAEs is the lack of conditioning to impose specific constraints on the generated data. With Kingma's original work, we can't really generate a specific image. Fortunately, many research papers have tried to address these challenges, resulting in several advanced VAE models designed to overcome these limitations. Some of the more notable variants include conditional VAEs, which allow for a class-specific image generation, beta VAEs, which introduce a tunable parameter to control the trade-off between reconstruction quality and disentanglement, and vector-quantized VAEs, which provide a discrete latent space for sharper reconstructions. We'll explore each of these models in future videos, so stay tuned if you want to know more. Thank you so much for watching this video. If you enjoyed it, please like and subscribe to help me grow the channel. The next video will be about contrastive learning. See you in the next video. So let's note Q of z given x the approximate posterior distribution. Our goal is to sample new data from the original data distribution, so we need to pick a sample x that maximizes this probability. Well, let's start by marginalizing the log density of the data distribution. We then introduce our approximate posterior using this simple trick. This allows us to rewrite our expression as the expectation of this ratio over our posterior. Now, because the log function is concave, we can apply Jensen's inequality, which gives us this final inequality where the log and expectation have been swapped. The right-hand side of this inequality is known as the evidence lower bound, or ELBO. It is indeed a lower bound to the quantity on the left, which is called the evidence. So, if we want to maximize the evidence, we can focus on maximizing the ELBO, something that's much simpler to do. We can replace the joint probability in this expression using Bayes' formula. The ELBO then gets broken down in 2 main pieces. The first one is just the expectation of the likelihood over the posterior distribution. The second term can actually be rewritten as the Kullback-Leibler divergence between the posterior and the prior distribution P of z. And just like that, we end up on the loss function used to train the variational autoencoder.